So, good afternoon. I am Krishna Kumar. Let me first thank Dr. Abbas for extending me an invitation to talk to you this afternoon. It's always a pleasure to talk to an academic community. Well, today's topic is related to the existential uniqueness theory of ordinary differential equations, which most of you are familiar with. So let me first present the problem and then try to find a way of solving it. Let us recall a few facts. See, let D be an open connected domain in R. Now, I am assuming that f is a real valued function on D which we assume is continuous in both the variables. We also assume f is Lipschitz. This condition we are going to take out when we take up the problem. Lipschitz in Y on, which means the following, that is f of x y1, f of x y2 that means we are assuming continuity along the vertical line in the, see, this is B in R2 state. Then you are assuming that on the vertical line we are assuming this is continuous with respect to Y. And the specific estimate of the bound of f of xy1 minus f of xy2 is bounded by a times mod y1 minus. Okay, so this is the so-called Lipschitz condition, and you know that it is under the assumption that f is Lipschitz, which most of the functions that we deal with do satisfy. We prove that the solution to the ordinary differential equation or the initial value problem y derivative equal to f of xy defined on B with the initial data y0 where x0 y0 is a point. So you have some point x0 y0 given in here, which is the initial data for it. Now let us recall the following. We are interested in talking about the local solution. That means in the neighborhood of the point x0, something like x0 minus h to x0 plus h, you want to say that there exists a function which satisfies this differential equation and the initial data okay, on that interval mod x minus x naught less than h. So let me set that. So let S be the rectangle such that mod x minus x naught mod A and B are some positive numbers. such that S is contained in B. So you see that this is an open connected region, therefore x naught y naught is an interior point, so there exists some rectangle which is fully contained in this region. That is no problem. So this is the rectangle point. So this is so this height is B, this is A, this is C. So this is the x-axis. So on this we have, this is the point x naught 0, this is x naught minus A, this is x naught plus A. So it is on this interval that we are seeking a solution of this equation, satisfying the initial data x naught y naught. That is, at x naught y equal to x naught is equal to y. Okay. So the existence and uniqueness theorem that you have seen the proof of this using Picard's approximation method and then some estimations and so on. I am not going to do that, but probably I will do go through some of those arguments later on when I knock off some of these conditions in earlier estimations. Okay. So there exists H positive such that H is taken as is less than the minimum of A and B by M. Incidentally, we are on this, we are assuming M is the supremum of mod F on B. So we assume that it is a bounded function. This is supremum taken. So M, A and B by M. It's a very generous estimate that we are doing here. Then this equation, why there exists a function from x naught minus h2, x naught plus h to R such that x, y, x belongs to B and y is differentiable exists and y derivative of x equal to f of x y x for mod x minus x naught less than and further y of x naught, that is the function y, there exists a solution to the initial value problem. Now this is the initial value problem that we are working. So there exists a unique solution for this initial value problem. The solution is unique. Now recall this example. This is often quoted in the classrooms. Look at this equation. One by 3. The initial value problem y0 equal to 3. That means the initial data is what is called 0, 0, and you are seeking a solution of this equation on whose graph would pass through the point 0, 0. Now you have seen that, or it can be directly verified that y x equal to 0 for every x is a solution which satisfies this. Okay, so that is one solution. The second solution is yx equal to 2 by 3 x to the power 3 by 2 for x greater than or equal to 0 and taken as 0 for x plus x. And now the graph. See, this is the one solution is identically equal to 0. We mark by a colored chalk. So this yellow line is the graph of the solution, y identically equal to 0. The other solution is up to 0, this is the x-axis. Up to 0 it is 0, and from then on it is something like this, it starts taking off. So there are in fact two different solutions, two or more than two also, solutions for this equation. It is not unique. So the initial value problem does not have a unique solution. And one can show that the solution is correct. And one checks immediately that the function does not satisfy Lipschitz condition. In any neighborhood of no matter how small a neighborhood, doesn't satisfy as long as this. In fact, you can see that this can be, if I change the initial data as y x naught equal to 0 for some x naught, then a similar thing happens. So you see that there is something that goes wrong in the neighborhood of the x-axis. For the Lipschitz condition, in no neighborhood of x-axis, the function satisfies the Lipschitz condition. This is the problem. Okay. So the uniqueness breaks down here. So our question starts here. So what we ask for is this: is it possible to, as you have seen here, the solution exists here. To show that the initial value problem has a solution without asking for what is called uniqueness. You know that for uniqueness you need some extra conditions. In the absence of Lipschitz condition. Probably not very often discussed in the classroom. We are going to explore this problem. It is in this context. See, I have a dual purpose for this talk. One is to show an application of a tool that we developed in a course on analysis, namely the Ascoli theorem. It's talking about functions, a sequence of functions which satisfy the equivalent condition. Then it says that there are subsequences of that which converge, and there may be more than one subsequence which converges. Now, I want to highlight, draw your attention to the importance of that. So that's the purpose. Okay, so this is the question that we start. Right. So we start with our problem. Y derivative equal to f of xy, yx not equal to, all those conditions are defined there, not assuming f functions. Now, how to work a solution of this problem, to investigate whether it exists or not. Now, let me develop some proofs. Before I embark on the proof of this, I'll tell you exactly what Ascoli's theorem talks about, and then we'll see how they can be linked with it. Okay, let me start. Let me start with before. We start with the vice versa. Or sequences or boundaries. See, you recall that every bounded sequence in R has a convergence of sequence. Says has a convergent subsequence, which does not rule out the possibility of having more than one convergent subsequence. So what happens is, on a compact subinterval, that's a closed bounded interval of the real line, if you were to choose an infinite set of points, then it is possible that it has a limit point. It has to be closed and bounded, and all these are equally important. Now I am not going to go for a deeper discussion of that, but you can see that if you were to take the interval 0, 1, open interval 0, 1, and then consider the sequence 1 by n, it has no convergence subsequence. The sequence itself does not converge in that set, and it has no convergence subsequence. The reason is that it is not a closed set, okay? Although it is bounded, right? Similarly, you can work out an example to show that all these conditions are equally important. That's a small exercise. But what is important is the following. Now, we are going to seek a generalization of this result for a sequence of functions. Okay. This is where the story is clear. Yes, like this. Let me take out this. Sorry for the limitation of the space in the board. I have to remove certain. Suddenly they are recorded. work on this. Okay, so you have, if the sequence is to choose an infinite set of points in a compact subset of R, S A convergent subsequence. In fact, you may have more than one convergent subsequence. I give an example. The example that comes to my mind is the following. Consider this. The sequence AN defined by minus 1 to the power n, 1 minus 1 n. Now you know that the sequence is bounded, is lying in the compact interval minus 1 to plus 2. So we are on the interval minus 1 to. So what you have is that this has two subsequences, one that converges to 1 and the other one that converges to minus 1. It's not just, it's a bounded sequence and just two subsequences which converges to, one converges to 1 and the other one converges to minus 1. Just keep that in mind. Now what you have is the following problem. Suppose you have a bounded set, something like R2, let us take an interval. And suppose you have got real valued continuous functions defined on this interval A. Assume they are all continuous. They are all the graphs. So you have now a sequence of functions AB is a closed bounded interval. Now we assume the sequence Fn is uniformly bounded. That is, there exists M positive such that mod Fn less than okay. This is right. So it is. So you see that the graphs of the functions given by x, Fn x, lie in this particular diagram. What I have done. Now we consider the following problem. We ask the question, a similar question like this. Does there exist a function which is the limit of a subsequence of the sequence of functions? Okay. Secondly, we are assuming all these functions are continuous. Can you assure that it has a convergent a function converges, the subsequences converge to a continuous function. Now this is the theme of Ascoli. Says that you need a concept called equicontinuity to assure that the limiting function is a continuous function. Let us look at this problem. You take some point x on the interval A. Now if you draw a line, a vertical line, you see that the function Fn, look at the sequence and x. What can you say about the sequence? This sequence is bounded between minus m and plus m. So you have an infinite sequence for a fixed x. There is an infinite sequence of points lying between minus m and plus m. You can apply Weierstrass theorem to conclude that there exists a subsequence or more than one subsequence which converges on this. This is the important point. Now you see that it is true for every x on this interval. Okay? So you have got points corresponding to each x. There is a limit or what you call limit points of the sets points f and x. Now the question is, do they all patch up together to get a continuous function? Under what condition you can say that these subsequences which converge, that is clear, would sit together or stay together to form a continuous function? It is in this context that you need more than continuity of these functions to support this. So you need a concept called equicontinuity. And let me just define this. A set S of functions F is equicontinuous on the interval AT if given epsilon positive, there exists positive such that x1 AB or x1 minus x2 less than delta implies mod fx1 minus for every, this is the important in short, what happens is you have continuity, alright, but given epsilon there exists a delta. In general, the delta would depend on a particular x, but what we need now is that the same delta should work for every f in S. In that case, we say that collection of functions is equicontinuous on the interval. Okay. So the point is this, that we are putting the condition that for every f belonging to S. Now, if you are talking about a sequence of functions fn, suppose S is the sequence of functions fn, then we talk about the equicontinuity of this. Then you see that corresponding to epsilon, there exists a delta. That delta would in general depend on n. But what we want is a choice of delta should exist such that it is independent of n. So that for all s it is the same delta, or some way you are saying that at the same rate you have continuity or smoothness for all the functions in this collection. So this is equicontinuity. Now you see that we go back to the problem. So for each point set f and x, for each x, you have the convergent subsequences. The question that you ask is, do these convergent subsequence or the limit points patch up together to form a continuous nice continuous function. Says under the condition of equicontinuity, you can assure that this is true and that is the square. So let me just now write down the theorem. I write it as lemma because I use it in the theorem. That's all. An infinite set S of functions uniformly bounded that means it should be, the graph should be packed in some kind of a rectangle here, uniformly bounded and equicontinuous over a closed interval or in fact on a compact interval, because you are, it's a closed bounded interval that you are working with. Contains a sequence converting uniformly on AB, and consequently this the limiting function is a continuous function. The only problem is that you are only making a statement that it has a convergent subsequence, or it may have more than one convergent subsequence. Therefore, there may be several functions which converge exactly as the problem that you see on the if you take a bounded set of sequence, a bounded sequence of points on R as a convergent subsequence. You may have more than one. Now this can happen in this case. But the equicontinuity will assure you that there are two conditions: equicontinuity and uniform boundedness. Both these conditions put together would assure you that you have a subsequence which converges uniformly on once it is uniform converges, you see the limiting function. They are all continuous functions, therefore they are step. Now this is the tool that we will be using in answering this problem. Okay, so we are going to knock out this Lipschitz condition from our consideration. Okay, so let me just work out that. Make the statement as well. So I think the problem is clear. Okay. How do you say the problem is clear? So you have y dash is equal to f of x1. So we take S as the rectangle. Or x minus x naught less than equal to a, or y minus y naught less than or equal to. with the initial condition that y x naught equal to y. I am not assuming the f is Lipschitz. Now you see that you can apply the Weierstrass approximation. A lot of these tools that you have put in the toolbox of analysis is now coming into play. So we use the Weierstrass approximation theorem to conclude that Weierstrass approximation. Okay, let me just talk about the strategy. The strategy is, instead of considering the problem, the initial value problem here, we consider the following problem. Y derivative equal to pxy. Where p is a polynomial in the two variables x and y. Now you know that polynomials are nice functions. They satisfy Lipschitz condition. Therefore, you replace this problem by this particular problem with f replaced by p, where p is an approximation to f. And Weierstrass approximation theorem tells you that it is there. You will formulate this properly, then it will be clear. Then what happens is, you can now construct a sequence of problems. See, you can take a sequence of polynomials Pn which converges to f. Okay? And corresponding to each Pn, you have an initial value problem with the same initial data. Then you get a sequence of solutions, because you see that there the existence and uniqueness theorem can be applied because each Pn is satisfies the Lipschitz condition. So you get a sequence of functions y and x defined on the interval some mod x minus x naught less than h. The solution exists, that we know. There exists an x such that these solutions exist. So you get a sequence of functions. Now what you are expecting is this. See, you have this sequence of functions. At least there is some subsequence which converges, and that subsequence, the limit of that subsequence will be a solution to this problem. This is exactly the strategy. So approximating f by a polynomial and then seeking the solutions of that. You know that unique solutions exist for the initial value problem corresponding to the polynomials Bn. Now you just simply take the sequence, if possible, applying these things so that, see, the Ascoli's theorem is applicable provided this is uniformly bounded and equicontiguous. Under the given conditions, you prove that the sequence of functions satisfy those conditions so that it has convergent subsequences, and you show that corresponding to each corresponding or each convergent subsequence, their limit will be a solution of the initial problem. So it is built into the problem that there could be more than one solution satisfying the initial conditions. Or the initial value problem may have more than one solution, as we have witnessed in the case of that example that we have looked at. This is the important. Okay, so let me just do this, and let me Weierstrass approximation theorem tells you that f of xy is continuous in a region R given epsilon positive, there exists a polynomial Pxy in the variables x and y such that Pxy less than epsilon, and you can even choose Pxy less than or equal to f. That means an approximation from below for xy. Good on you. Direct times r. So this is the Weierstrass approximation here for two variables. So what the strategy is, approximate f by polynomials. Polynomials are nice functions, they are analytic functions in fact. So they satisfy Dirichlet's condition, there is no problem about it. Differentiable as many times as you want, and so on. All nice things are there. So it satisfies all the conditions of the existence and uniqueness theorem. And if you take up the corresponding equation with f replaced by p, a unique solution exists. So let me just write down here. F of xy is continuous in there exists a solution of the initial value problem y dash equal to f of xy, y is not equal to, that's the initial condition, where x naught belongs to be defined by interval on x minus x naught less than equal to h, which is equal to minimum of where m is the bound for f on the interval on the rectangle. Mod x minus x naught less than or equal to a, mod y minus y naught less than or equal to a. So that is the theorem, that the main statement of the theorem. Okay, let me just outline the proof of this theorem. I have about 10 minutes, so I'll just give you an outline of it. I have already given you the strategy. The strategy is to construct a sequence of functions, do that it's equicontiguous, it's uniformly bounded, then there exists subsequences which converge. And the limit of each of these converging subsequences will be a credible, valid solution for the issue. So let me just take out this. what we do is we take Pn xy as a polynomial sequence. This is sequence of polynomials. R is the rectangle, mod x minus x naught plus n equal to a, mod y minus y naught plus n. Or you can even take this defined on E. Okay, such that mod the Lorentz. Then M is the bound for F or okay. So this is a rectangle. So this is x naught by naught, and this is x naught minus x naught plus x. So it is on the interval x naught minus x cube, and it is on this rectangle that you have Pn approximately within the error of epsilon n. We choose epsilon n such that epsilon n goes to 0. That's it. So what happens? Now you look at this. Because Pn is uniform. Pn is uniform. Now assume M is common bound for Pn as well as M. So Pn xy which is on Theorem 10. That is because they are polynomials. Polynomials are just functions. So you can easily prove that they are same functions. Therefore, now you look at the sequence of yx y derivative equal to so that gives a sequence of functions y and x defined for mod x minus x naught as solutions of, as unique solutions of yn uniquely determined solutions. Now what we prove is that the sequence of functions yn is independent. They are uniformly bounded by R. There is no problem. Now you see that mod ynx is y naught, this is y naught, is less than or equal to n h. Therefore, mod that is uniformly bounded. So now we prove that it is equicontiguous. To prove that it is equicontiguous, what one uses is the following. Because you see, you take x1 and x2, you observe that yn x1 minus yn x2 is yn x2 minus, is it like that? You apply the value here. This is equal to some intermediate point psi this was a basic. But yn dash psi, this is equal to mod en psi and this is less than or equal to. Therefore, what you have is equal to n mod. Let's see this also. Now you see that this m is equivalent. Therefore, what we have is that given epsilon positive, for mod xn mod x2 minus x1 less than or equal to delta mod ynx minus yn less than or equal to therefore, you see that this is uniform or equicontiguous is assured. And so that x2 after x1 after this condition is satisfied, then this is one. So hence it is equicontiguous. Now what one does is this. You see, you observe that the following. So there exists a subsequence We are applying earlier theorem. Converting uniformly on a continuous now this for each subsequence you can give a y. It's not see there may be more than one subsequence which has this property, but let us see what happens for one such function. It has a limit. That's the limiting function is yes. Now we claim yes solution. Now this is again once again the technique that we use here is exactly the same as what you do in the proof of this. So what you have is this with the following, and you see you have this initial value problem converted into integral equations. This is the equivalent integral equation. So you prove that there's a solution. So essentially what you do is you choose this. You see that corresponding to each epsilon n goes to 0 as n tends to infinity. What you do is you choose these functions yn. Okay, subsequently convert this to y. Therefore, what you observe is that limit n tending to infinity of integral now you see this proof does not depend on, need not use this what's called Lipschitz continuity. Even without Lipschitz continuity, you can prove this. This means that you are moving this inside and once again inside the function, and all these things can be justified. So this limit can be shown to be equal to this. Now what one does is you have the approximately initial value problems. From that, you go to the limit. So let me try to wind up this talk. Now I think this is almost time. So I just write down the steps. So you have actually ynx minus y naught is equal to integral x dot x en t hence x dot x mod minus mod dt. Now from this estimate, now you see you have got Pm is less than epsilon n, and epsilon n goes to 0 as n tends to infinity. Therefore, Pn converges uniformly to f of xy on the interval mod x minus x naught. Use that. Use that, then you get mod therefore you have mod yx and that is the function y, which is the limit of the subsequence which converges, satisfies the integral equation and for the initial transfer. So that's the thing. In fact, the important part is that one cannot assure that there is only one such limiting function under the assumptions that we have taken. So, in the absence of Lipschitz condition, you may get more than one solution which satisfies the initial transfer. I think I have made my points here. Thank you very much. And this is a nice opportunity given to me. I once again thank the organizers for extending this invitation. Thank you very much. I will join you at the Google Meet. Hello, I am on the Google Meet. Yes. Hi, Abbas. Hello. Nice to meet you. Hello.
So my question is ultimately we are using this criteria for this monomials.
Yeah.
So they are not building this function, they are quite monomials.
Yeah.
So my question is, so it is not true that your these functions, the limit is also is.
No. See, these polynomials are smooth functions, but you don't need that much of restrictions on f. See, f you are assuming, not assuming Lipschitz. So the limiting, see, what is the condition that you have in the Weierstrass approximation theorem? So this the limiting function need not be a Lipschitz. This is the point. So you can take this function approximated by polynomials which are smooth functions, see, which are even analytic, whereas your function may be just assumed to be only continuous in the two variables. That's all. That's the advantage that you get.
Yeah, and we are losing this uniqueness.
So once you drop that Lipschitz condition, you lose your uniqueness,
So
which is
anything other than this case that will give me uniqueness? This is very
no, I don't know. I haven't seen anything, but certainly this is only a sufficient condition. Or to the best of my knowledge, it's a sufficient condition. It's not a necessary and sufficient condition. But certainly, in the absence of some such conditions, one cannot assure uniqueness. As you know, there are several examples that you can construct where it is like this. But I have not seen any sharp condition which tells you this. Anyway, it is very nice to see you from a distance. It's wonderful. Okay.
Thank you, sir, for this nice talk.
I thought I was clear, no? With my lecture. Yes. Okay. That's nice. I'll certainly visit Varanasi sometime. Yes.
Thank you, sir. Thank you once again.
Thank you very much. Okay.